This I'm stuck in this video, we are looking at statics. So statics is the study of forces in equilibrium, and this means that the resultant force acting upon it is zero. And when the object is just about to move, friction has its maximum value, which is called limiting friction. And the coefficient of friction can be used to calculate the friction, so the higher the coefficient, the more friction there is, as friction is modelled by the coefficient of friction times by the resultant force. So here we have a question. It says that a boy sits on a sledge on horizontal ground. The combined weight of a boy and the sledge is 750 newtons. A friend pulls the rope attached to the sledge so it makes an angle of 10 degrees to horizontal. So let's draw a model of that so we can see what's going on. So if we have our sledge here, and that is 750 newtons, which means it is exerting downwards a force of 750 newtons downwards, and then upwards we have this resultant force. Then we have somebody pulling a rope attached to the sledge so it makes an angle of 10 degrees to the horizontal. So that means that we have somebody with a rope, and that's 10 degrees there. And that's the rope there, and we'll have to see how much this rope is in a second. Then obviously on the way back, it says when the sledge is about to slip, the friend is pulling with a force T. The normal reaction of the ground and the block is R, which we have there, and the coefficient of friction between the sledge and the ground is 2/3. So coming on the way back, the resisting force, we have 2/3 R. Now we've got that because, as I said before, F is equal, so F friction is equal to the coefficient of friction times by R. So that's why we have 2/3 R there. So then we know that he's pulling with a force T, so this is a force T here. So then we've got to resolve this forces. And over here, that's opposite, so we're going to have T sine 10. And then here we have T cos 10. So now we have that. Now we need to show that T is equal to 450 newtons, and then we need to find what R is. So we'll start off by resolving it vertically and horizontally. So if we start off by doing vertically, what we're going to get is we're going to get everything which is vertical, so that's going to be R, and then we got T sine 10, so it's R plus T sine 10. And because it's in equilibrium, the forces up are going to be equaling the forces down. So R plus T sine 10 is going to be equal to 750. Then if we go horizontally, now we have 2/3 R, and that's going to be equal to T cos 10. So using this one here, we can find out that R is equal to 750 minus T sine 10. So therefore, we can substitute R into this one to here, so you get 2/3, and then 750 minus T sine 10 is equal to T cos 10. Doing some rearranging of this, what we're going to get is 500 is equal to T cos 10 plus 2/3 T sine 10 and then what we can do is we can take out a T, so 500 is equal to T, and then we've got cos 10 plus 2/3 sine 10 which means that t is going to be equal to 500 divided by cos 10 plus 2/3 sine 10. So t is equal to 454.3 newtons, which it says here t is equal to 450 newtons to two significant figures. So to two significant figures, this is 450 newtons. Then it asks us to find r. Now this is fairly easy as we already have an equation here for what r is. So we just have to sub that in. So therefore we can say that r is equal to 750 minus, and then we'll be using the actual value of t, not the simplified one. So 454.3 sine 10. So therefore r is equal to 671.1, which is 670 newtons to two significant figures. So the next question says a box of weight W lies on a rough horizontal surface. So again, what we're going to do is we're going to draw a diagram of this to show what it's trying to say. So we have this is on a rough horizontal surface. This is W. And then it says that it's attached to a crate and pulled at 20 degrees above the horizontal. So therefore, we have it here, it's pulled at 20 degrees above the horizontal. And that is with a tension of a half W. So therefore, that's a half W. So what we're going to get here is a half W sine 20 and then here a half W cos 20. So now we have that. What we need to do is look at the rest, and since that the box is just about to slip, which means it's just about to move, the normal reaction of the surface on the crate is 30 newtons. So the normal reaction is coming up here. That is 30 newtons. And the coefficient of friction between the box and the surface is this coefficient of friction, it's mu. So that means that what we're going to have here is 30, because it's going to be the coefficient of friction times by the resultant force, and we know the resultant force is 30 newtons. Going down, we have W. So we'll start off by working out what W is. So that means that we'll both resolve horizontally and vertically. We'll start off with vertical, which means that what we're going to get there, we're going to get 30 plus half W sine 20 and that is equal to W. Now from this we can work out what W is, because we're going to get 30 is equal to W minus a half W sine 20 so therefore 30 is equal to W minus 0.171 W. So 30 is equal to 0.829 W, which means that we can get W by doing 30 divided by 0.829. W is equal to 36.2 newtons. So now we have W. Now we need to resolve horizontally in order to work out what the coefficient of friction is. So that means that we're going to have 30 mu and that is equal to a half w cos 20 sub in what w is. We can sub in 36.2 for w there, and we can get 30 mu. That's equal to 17, which means that the coefficient of friction is equal to 0.567. That's to 3 dp. So the next question, we're looking at an inclined slope. It says that a block of weight W lies on a rough slope inclined at an angle of 10 degrees to the horizontal. So if we were to draw this time, instead of a horizontal slope as we've had in the last two questions, we have a rough slope, then we have this is our box, and this is weight W. And that's our rough slope, which we can extend. And that rough slope is at an angle of 10 degrees to the horizontal, like that. Then it says that the coefficient of friction between the block and the slope is mu. So a string is attached to the block and is passed over a pulley at the top of the slope. So this time we have a pulley here, which is going to look a little bit like this. And then we have our weight here. It's attached to the other end to a block of weight a half W. So therefore that is going down there, a half W. Which hangs vertically. So the block of the slope is just about to slip up the slope. So it's just about to slip up, which means that friction is going to be acting down. And that means that friction is going to be, we've got just going to be mu r. So we don't know any of those at the moment. Now we know that weight is going to act straight down. So this is the problem sometimes with something which is on a slope, as weight's going to act straight down. This means that we're going to have to resolve weight so that we can get vertical like this, which is perpendicular, and vertical like this. Now the first trick is to work out what this angle here is. And this angle will always be the same as this angle here. So that's going to be 10 degrees there. That means that this point here is going to be its opposite, so it's going to be W sine 10. And this one here then will be W cos 10. R is going to act like that, so we don't need to resolve that. It's just weight which acts straight down like that. Then in this one here, we're going to have tension. So the pulleys, we're going to have tension here and tension here. So therefore, what we're going to start off by saying is we'll start off by resolving it vertically, and we have to resolve perpendicular to the slope. So therefore we've got R is going to be equal to W cos 10. So you got R there, and you got W cos 10. Those are perpendicular to the slope. That's why we had to resolve it there. So now we've got R is equal to W cos 10. Now we can do it horizontally. So we have the coefficient of friction times by R. And that is going to be equal, well, we actually have to plus then a W sine 10. Because we've got those two things acting horizontally. So plus W sine 10. And that is going to be equal to T. Now we can work out T because it's going to be, we've got this and this. So T is going to be equal to half W because they're in equilibrium. So that must equal that. So therefore, as T is the same there and there, that means that T is going to be half W. So then we can put half W. So now we've got that, what we need to do is rearrange this. And we can rearrange it by saying that R is equal to W cos 10. So therefore what we're going to get is W cos 10 mu, and then plus W sine 10 is equal to half W. Now we're working out what W is first, as we cannot just work out the coefficient of friction without W. So that's why we're doing this first. So therefore, what we're going to get is we need to find out what mu is. The coefficient of friction is therefore equal to a half W, then minus W sine 10 over, and then it's going to be W cos 10. If we take a W out of here, we can say that this is equal to W, and then we've got a half minus sine 10 over, and then W cos 10. And hopefully what you've seen here is that we can cancel this W here, we can cancel this W here. So what we're left with is a half minus sine 10 over cos 10. Therefore, all we have to do is put that into our calculators, and we will get that the coefficient of friction is equal to 0.331. So the final question we have says that two particles of weight kW and W are connected by a light inextensible string which passes over a smooth fillet fixed at the end of a rough horizontal platform. The kW weight rests on the platform and the W weight hangs freely below the pulley. Find the coefficient of friction in terms of K between the kW weight and the table if a system is in limiting equilibrium. So here in this question we'll do a diagram to show what's going on. We have a horizontal table here. This is a horizontal platform, which is rough. Now rough means there is friction. Then what we're going to have is this weight of kW rests on the platform. So you've got kW here. This is going to be kW down. And then up, we're going to get R. Then this way, this is our coefficient of friction. We've got the coefficient of friction times by R. And then this way, we have a pulley. So it says a smooth pulley fixed at the end of a rough horizontal platform. So we've got this pulley here. And then this is where we have the weight W hanging freely below the pulley. So you've got W here, so that means W acting down here. So therefore, what we've got here is we've got tension coming up here. We've also got tension acting this. Again, we're going to use the same trick. We can work out that T, tension, is equal to W. It's in equilibrium. It says here, limiting equilibrium. So friction is at its maximum value. So T is equal to W. So therefore, if we want to resolve vertically to start off with, we can say that R is equal to KW. Then if we want to do it horizontally, we'll say that the coefficient of friction times by R is going to be equal to W, as T is equal to W. Therefore, we can get that W is equal to R divided by K, and this is using this here by doing divide it all by K. So W is equal to R divided by K. So therefore, using that, we can get that W is equal to the coefficient of friction times by R. So that means that the coefficient times by R friction is going to be equal to R divided by K. This means that the coefficient of friction is going to be equal to R over K divided by R that's going to cancel, that's going to cancel. Therefore, our final answer in terms of K, as it asks us in the question, is the coefficient of friction is equal to 1 over K. So thank you for watching this video and see you soon. Bye.